Okay, just like I had on the first lecture for homeostasis, I've got a little cartoon on the front page of this lecture. It's not a cartoon that's meant to be funny, but it's meant to serve a purpose and explain kind of an important concept that we're going to be talking about in this lecture. Okay, so to kind of explain the picture, we got some bubble dudes inside of a classroom, teacher at the front, trying to teach them, but the bubble dudes are not so interested in what's going on in the classroom. Instead, they are concerned with the pretty bubble ladies outside of the classroom. If you look inside of each of those little fellas, there's a positive symbol. The plus sign represents positive. And outside, you can see the ladies have a negative symbol associated with them, which demonstrates something that you may have heard regarding lovers and people that are in love, that opposites attract. Okay. Now, we don't quite understand what that means yet, but there will be a point in this lecture where I'll say, remember that first page. So we'll refer back to that later on. Before we get to any of that, let's just define what chemistry is and stuff associated with chemistry, which includes matter and mass and weights and elements and atoms and all sorts of different things. So I'll give you guys a second here to write, and then we'll talk. Okay, chemistry is defined as the science of the structure interactions of matter. Matter obviously is very important to chemistry, so let's define it. Anything that has mass and occupied space is classified as matter. So it's anything in and around us, okay? So it could be the water that's in our Gatorade jug or my jug up here, the table that you're sitting at, the air that's around us. We ourselves are a form of matter as well. Okay. Matter, once again, is anything that has mass. So mass, to define it, is the amount of matter in any object. And the key thing here is that it does not change. Okay. Whereas weight is the force of gravity acting on matter and can change. A lot of times you see people and hear people use mass and weight interchangeably. Okay. Chemistry-wise, that is very incorrect. The amount of us doesn't change. Our weight can change. So a great example of this would be like comparing mass and weight on Earth to mass and weight on the moon. Does the amount of us change when we go to the moon? No, but if you were to step on a scale on the moon, would your weight be the same there as it would be here? No. Why is that? There's less gravity on the moon. It'd actually be kind of difficult to stand on a scale on the moon because you've seen videos of astronauts, they kind of bounce around. And there's very little gravity on the moon compared to here. Now, as far as matter goes, there's three phases that it can exist in: solid, liquid, and gas. Okay. There's one especially very important form of matter to all living things that actually here on Earth comes in all three phases. What am I talking about?
Water.
Water. Very good. Water, the drinking form, is obviously a liquid. What's the solid form of water? All right, what's the gas form of water? The gaseous water that's in the environment around us. When water evaporates, it goes into the atmosphere as gas. Good. Okay. All forms of matter, whether we're talking living and non-living, are made up of atoms, which is the smallest stable unit of matter. We introduced atoms a little bit the other day when we were talking about the levels of organization. We're talking extremely small here. Now this last sentence in this second or first bullet is actually incorrect, but I keep it in there to emphasize how amazingly small we're dealing with. 200,000 of the largest atoms would fit on the period at the end of the sentence. It's not incorrect as in this is a completely false statement. but when I took this sentence, it was from the textbook. Textbook's font was like 12 points. This is much bigger than 12-point font. So it would be even more atoms. But that still demonstrates how small we're talking here. Itty, 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 bitty. Okay. We talked a little bit about the periodic table the other day. We're going to talk a lot about it here today, which is where the elements of the body, or excuse me, of the world, which includes our body, are organized. An element is a type of matter that cannot be broken down into two or more pure substances, and it is matter composed of only one kind of atom. Okay. Compounds are pure substances that contain more than one element, like water, which is also known as what? H2O, very good. Okay. And it's important to understand that compounds have a fixed composition, meaning that H2O is water, H2O2 is not water, H3O is not water. The only way to make water is to put two hydrogens and an oxygen together, and there's your water. Make sense? Okay. Let's talk more about elements and atoms. All right, in our top left corner here of the page, I know yours is very small, but that's okay. I'm going to include the entire periodic table. If you want one of those, you can go to Google, or there's one in your textbook. And this is the very top left corner of the periodic table. I'm going to talk and show some different things that we see that make up each of the boxes in the periodic table. Defining element, again, it's the simplest form of matter with unique chemical properties. Periodic table, which is actually short for periodic table of elements, can be used to organize basic information about the elements of our universe. Okay. Included in each of those boxes will be three major things. The abbreviation for that element, which is always going to be at least one letter, and that letter would always be capitalized. And then if there's two letters, the second letter is always going to be lowercase. Okay. A lot of times it's the first one or two letters of the word of that element, like H for hydrogen, okay, which is super simple. Sometimes it gets a little bit more complicated, and this relates to Latin roots in many cases, like Na, which is actually the abbreviation for sodium, which sounds really stupid and weird, but that's what it is. Okay, Au is gold, if I remember off the top of my head. Okay, another example of that. Potassium is not P, it's K. Some of them we will learn really quickly, and you'll know them right off the bat when you see them, but it's not like I'm going to ask you to know the entire periodic table, okay, and their abbreviations and whatnot. Above that letter or two letters is a number. That is the atomic number. Okay, that bullet there that talks about atomic number might be a good idea. Somewhere next to it, put in parentheses, top number. Okay. The bottom number is the atomic mass. Might not be a bad idea to put in parentheses the bottom number next to it. Those tell you a lot about an atom of those elements. Okay, we're going to talk about the structure of atoms here in a few slides, but there are three major things that are found in an atom: protons, neutrons, and electrons. And those numbers are going to tell you about, or those numbers are going to tell you about the protons, electrons, and neutrons. The top number tells you the number of protons in one atom of that element. So how many protons would be in hydrogen? 1, because its atomic number is 1. The bottom number is the number of protons plus the neutrons. Now, you'll notice it's not a perfect round number, but it's dang close to it. Okay, like beryllium, which is 9.01, da-da-da-da-da. Okay, you can just round either up or down. So how can you use the bottom number to find out the number of neutrons in an atom of beryllium. You know the top number is protons, the bottom number is protons plus neutrons. So if I asked you how many neutrons are in beryllium, you would take the bottom number and do what? Subtract the top number. So how many neutrons are in beryllium? 9 minus 4 is 5. Very good. Does everybody see and understand that? Very good. Okay. Now we'll talk about electrons here and what numbers of those here after a bit. As far as the elements, there are many of them, but only 26 of them really play a role and are present in our body. But of those 26, really 4 are the big dogs. I told you this the other day. Remember it? CHON, CHON, carbon, hydrogen, oxygen, nitrogen are the most prominent. We call those the majors. They are representing about 60 or 96% of us. Then you've got 8 others, which are lesser, to make up 3.8%. This includes calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, and iron. And then there are 14 trace elements, but they're so small. Collectively, together, they're only 0.2%. So they're very, very minuscule. Each of those different elements, though, is very important to the body in their own right, which is why I included table 2.1, which lists off the 4 majors. Notice it's not in the correct order. Like I said, CHON, because carbon is actually not the most prominent element in our body. Oxygen is, and by far and away, oxygen is the most, at 65%. And then it goes all the way down to iron for the lessers. Lists off their percentages and what they do as far as significance goes, which is not something I'm going to worry about, in this table. I just included it because there's some good information in there, but I'm not going to ask you anything specific to it. All right, let's talk more about atoms. Okay, a single atom of a given element contains several different kinds of subatomic particles, which give each element its unique chemical properties, meaning each of those boxes in the periodic table, once again, each box represents a single atom. Each of those elements have different numbers of protons, electrons, neutrons, and that's how they're all unique and different from one another. Okay. Those 3 important subatomic particles are either found within the nucleus, which is the dense core of an atom, or surrounding it in shells, rings, layers, whatever you want to call it, which is where the electrons are. The protons and neutrons, which we were just talking about, are found in the dense core of that atom. And you can see here on the next page a couple different ways to illustrate the structure of an atom with the protons and neutrons inside. And that's where, once again, the mass of an atom comes from, which is why atomic mass is equal to protons plus neutrons. And surrounding the central core of an atom, that nucleus, are these rings or shells or clouds, whatever you want to call them, which is where the electrons are. Electrons are very tiny, and they don't even really register any weight for the atomic mass. Think of them comparatively to us like gnats flying around us. Okay. They circle around us. We would be like the nucleus. The gnats are so small and tiny that you couldn't weigh a gnat and it would register anything as far as like pounds go. The electrons, protons, and neutrons all elicit a different charge. I go back to this previous page. Think P for positive, P for protons. Each proton elicits a +1 charge. Okay. Neutrons, I always tell students, think neutral neutrons. What's neutral mean? It's not positive or it's negative. It's +0. Okay, you can say -0, same thing. It's just 0, no charge for neutrons. And then electrons are negatively charged. Each electron represents a -1 charge. Now, when you look back at the periodic table, that top number tells you the number of protons. But it might also be a good idea, go back and right next to atomic number, it also tells you the number of electrons. So atomic number not only tells you number of protons, it also tells you number of electrons. And that creates what we call an electrically neutral atom, which means what? Electrically neutral means that it's zero charge. There's no positive, there's no negative, because there's equal positives and equal negatives. Okay? So like here we show, this is carbon, I just know that because there's 6 electrons. There are 6 protons, I don't think you can see them all in the picture. There's 6 pluses, there's 6 negatives. What's 6 plus minus 6? 0, right? And that's a neutral atom. Okay. All the atoms in the periodic table in that state are neutral. So the top number not only tells you protons, but it's also going to tell you the number of electrons. And now, those electrons, as you can see here in these 2 figures, especially this one on the right, are found in these rings or shells or layers, whatever you want to call them. Like I said, each of those rings can only hold a certain number of electrons. Okay? The first ring can hold a number of 2. The second ring can hold 8. Okay? In this case, carbon is only having 4 in its outer shell. Okay? But it could hold up to 8. If there was more, then there could be a third ring, and that can hold up to 18, so on and so on and so on. We don't really deal with too many because those aren't really important to us. Now, when we talk about filling up shells or rings, whatever you want to call them, we always start from the inside out. So always put the first 2 in the first ring, and then you go from there. All right, let's talk isotopes. Which are described as alternate forms of an element. And what that means is in some cases, like in the case of hydrogen that's shown here, you search around the world, you could actually find that there's 3 different types of hydrogen. Hydrogen 1, hydrogen 2, hydrogen 3. Protium, deuterium, and tritium, I believe is their actual names. The difference relates to the number of neutrons. Okay, so that means its atomic mass is different. Differs in mass. Once again, remember atomic mass was the number of protons plus the number of neutrons, right? Okay. The atomic mass of hydrogen 1 is 1 because there's 1 proton there. Is there any neutrons? There's just the 1 proton. 1 plus 0 is 1. What would the atomic mass of this be? 2. 1 proton plus 1 neutron is 2. 1 proton, 2 neutrons. Atomic mass of hydrogen 3 is 3. Okay. Now, as far as what you find in the periodic table, they always put the most common example, what you find most. Okay. The most common form of hydrogen is that hydrogen 1 with its 1 proton and no neutrons. Make sense? Something in the 90% is hydrogen 1. You find that way more often than the others. Carbon, there's carbon 12, 13, and 14, if I remember right. Just alternate forms sometimes. We don't talk much about isotopes. Really, that's about the only time. And then this slide as well, where we talk about radioisotopes, which are described as being unstable isotopes. Why are they unstable? Because radioisotopes over time break down, or decay as it describes them as, and in doing so emit a lot of radiation, or very high energy. That's what's radiation well known for? Causing what? Cancer. Okay. Turning people into superheroes in movies, that kind of stuff. It doesn't actually take place. It destroys our body. Okay, whether that's UV radiation that you get from the sky, or radiation from other sources. Okay. Anybody ever heard of Chernobyl? Okay. Last summer, I think HBO did a series on it. It was like a 10-episode series. Chernobyl was a nuclear power plant. I think it was in Ukraine. Had a meltdown, and essentially a lot of radiation was emitted because of that. And at the time, people that were living there were exposed to a lot of radiation. That's what happened to those people. A lot of them died almost instantly. Some of them, it took a while. Okay. This was like in the 80s, if I remember right. They evacuated people finally after a couple weeks. They told the people that they would be back in a few weeks. You're not allowed to go in that city without government approval and hazmat suits still to this day. It's because a lot of times these radioisotopes take, in some cases, hundreds of years to decay, and the half-life is what it says there. Is time required for half of that radioactive atoms in a sample to decay to a more stable form. So it's very, very, very dangerous to go there still to this day. Now, as far as radioisotopes, obviously that's a bad health situation, but doctors and scientists have actually utilized radioisotopes in a really cool way. They call them tracers. You can inject these tracers into the body, and it kind of helps highlight something that's wrong when you perform like certain scans. So it can help figure out and help a doctor perform that diagnosis that we were talking about, detecting certain diseases in the body. And that's what this table on the far right is illustrating. Not something I'd ask you to know, but kind of cool. Still the same. All right, let's talk molecules and compounds. When two or more atoms share, and notice I italicized the word share, electrons, they form what's called a molecule. Okay, and we'll talk about sharing electrons next week when we get that far into this lecture. Molecular formula indicates the elements and the number of atoms of each element that make up that certain molecule, like O2, which we best know as oxygen gas, specifically. You couldn't just say oxygen because that could be just an atom, because oxygen gas, O2, represents that there's two atoms of oxygen. That sub 2 there behind the O tells you that there's two atoms in that molecule of oxygen. Okay, that's an example of a molecule where it's the same element. Oxygen and oxygen are the same element. Doesn't always have to be the same element, like H2O, which we all know is water element. Hydrogen, two atoms of that, one atom of oxygen. You could put a singular number 1 behind the O for oxygen. You don't have to. Most of the time, it's just known that if there's no number, it's just 1. Okay. Anybody know what C6H12O6 is? Very good. Glucose, or sugar, which is super important to us, and we'll talk about that next week. Compounds and molecules really, truly are not technically the same thing. If Mr. Graham was over here, he'd probably yell at me for telling you this, but I use these terms kind of interchangeably. I'm not a chemistry guru by any means. Difference is compounds contain atoms of 2 or more different elements. Okay, meaning that water and glucose are considered compounds because they are different elements. Oxygen is not. Makes sense because oxygen gas is strictly oxygen elements. Element, I should say. Now, most atoms in our body are joined into compounds like water, H2O. Anybody know what sodium chloride is? Table salt, NaCl, 1 sodium, 1 chloride joined together. Now, when we join these molecules and compounds together, and we haven't talked about this yet, we're doing it for a specific reason, and that's to achieve stability when it comes to numbers of electrons. We're trying to fill up shells and rings. When we do so, there are times where we actually don't achieve chemical stability, which is an example here, free radicals. Electrically charged atom or groups of atoms with an unpaired electron in the outermost cell, or shell, excuse me, not cell. Over here on the left, we see an oxygen molecule where everything's nice and set up the way it's supposed to. Superoxide free radical here on the right shows you there's a singular unpaired electron. Think of these like a tornado. Very destructive to anything they come into contact with. And that's because of that unpaired electron, making them unstable, highly reactive, and destructive to nearby molecules. They do, and our body has the ability to make them stable though, which requires them to either give up their unpaired electron to or take an electron from something else. But in doing so, that can lead to breakup of body molecules. Free radicals, like radiation, are actually really well known for causing cancer. It is something that we do perform and produce free radicals all the time. Okay, but our body has special organelles that we'll talk about next week that help neutralize them. And lifestyle also is very helpful. Anybody ever heard of antioxidants before? You get a lot of antioxidants in fruits and veggies. Green tea is a great example. A lot of times, even if you buy a bottle of green tea or like pomegranate juice, you'll see great source of antioxidants. Antioxidants help neutralize free radicals as well. So eat fruits and veggies. All right, chemical bonding. Been talking about this for a couple slides now. We get to finally learn what it is, what goes into it. Defining chemical bonds, these are the forces that hold together atoms of a molecule or a compound. And the likelihood that an atom will form a chemical bond with another atom is all dependent upon the number of electrons in its outermost shell. So if I go back to this figure, really all you have to do to figure out if an atom is going to try to bond is look in these last, or this last ring. Shell, layer, whatever you want to call it. Okay, that's what we call its valence. Valence shell, valence ring, valence layer, whatever. Is always trying to achieve stability by filling its outer layer up. I always use the analogy of eating food and filling up your tummy. Okay? When your stomach is empty, you're not happy. Okay? You try to fill your stomach up to a perfect point. We try to fill up our ring to a perfect point. Okay? An atom with a valence shell holding 8 electrons is said to be chemically stable, meaning it's unlikely to form chemical bonds with other atoms. So we always want to have 8 in that outer shell, unless we are talking about 2 atoms, hydrogen and helium. And that's because that first ring, remember, how many could it hold? 2. Hydrogen has 1 electron, so it needs 2 to get there, or to be that point. Helium is actually what we call a noble gas. It already has 2, so helium is actually perfectly fine. It's eating a perfect amount of food. The octet rule states that atoms with fewer or more than 8 electrons in their outer energy level will attempt to achieve chemical stability, which can be done by transferring, which means electrons are going to either be moved completely away from or to that atom, or just by sharing electrons with another atom in its outermost ring. Okay. Octet means what? 8. Okay, so that's why it's called that octet rule. Chemical reactions enable atoms to give up or acquire electrons, thereby completing their outer electron shells. The way that they do so behave enables atoms in the body to exist in electrically charged forms called ions, or to join with each other into complex combinations as compounds and molecules. So let's go through these 8 examples and figure out what those different atoms would want to do, or if they're ready and happy where they're at. Okay, the first one we've already talked about quite a bit. Hydrogen has that atomic number of 1. Remember, how atomic number tells you number of protons, but it also tells you the number of electrons, right? Because positive and negative numbers are equal. Okay. In this state, is hydrogen satisfied? Is it full? Has it eaten enough? Is it hungry or too full? Using my stomach analogy. How many fill up that first ring? 2. Is there 2 in that first ring? There's just 1. Okay. So hydrogen is not happy yet, still a little hungry. Okay. So what could it do? It could gain 1, it could share 1. Sometimes hydrogen actually just gets rid of that 1 altogether. Okay. Carbon, atomic number is 6. 2 in the first ring. Remember, we fill from the inside out. That leaves us with 4 in the outside ring. Is carbon happy? No. What does carbon need? 4 more. Very good. Everybody see that? Nitrogen, atomic number is 7. 2 in the first, 5 in the outside ring. Is nitrogen happy? No, it would need 3 more. Oxygen, atomic number is 8. 2 in the first ring, 6 in the outside ring. Not satisfied yet. How many more? 2. Okay. Sodium, it's our first that has a 3rd ring. Okay. Atomic number is 11. So we filled up 2 in the first. Then there are 8 more in the second. The second ring is full, so we have to make a 3rd ring for that last electron. Okay. Is sodium happy? No, because the outer ring needs how many? 8, right? Okay. So what is sodium going to try to do? It can get 7 more, or what would be even easier than that? Get rid of that 1. Okay. And look at a good buddy of sodium, what we call chlorine. Atomic number is 17. 2 in the first, 8 in the second. That's 10, but we still have 7. 7 is not 8. Where could it get lucky number 8? From its buddy sodium. Okay. Potassium is just like sodium, except we've got a 4th ring. The 4th ring has just 1. So potassium's going to kick that 1 out. And iodine is just like chlorine in that it's going to need 1 more because it's got 1, 2, 3, 4, 5, 6, 7 in its outer, and it needs 1 more to get to that 8 number. Now, what happens to those atoms when they lose and gain electrons? They no longer have equal numbers of protons and electrons, do they? And that means they become ions. And we'll start with ions on Monday.